Today we're going to talk about polynomial functions and end behavior. So some vocabulary, the degree. The degree is the exponent on the variable in a term of a polynomial in standard form. The degree of a polynomial is the highest exponent on the variable of a term in standard form. And standard form for a polynomial is when the terms are in descending order from highest to lowest by degree. So here's the definition of a polynomial function, and where n is non-negative integer and the coefficients a sub n to a sub 0 are real numbers. So this would be our polynomial in standard form. So we can see we have this first term is a cubic term, so that's degree 3 because you have x to the third power. Then we have a quadratic term, linear term, and constant term. So notice that's in descending order with the highest power first. So that means this entire polynomial is a degree of 3 because that's the highest power of x in order. And the leading coefficient is a number that's in front of the highest degree, which is 3. So polynomials are classified by the degree and the number of terms it contains. A polynomial with one term is called a monomial, a polynomial with two terms called a binomial, a polynomial with three terms is called a trinomial. Polynomials with four or more terms are simply called polynomials. The chart below summarizes the names associated to polynomials by its degree. So if we look at this first example here, notice that this doesn't have an x, so really it's x to the 0 power. So that's why it says the degree is 0. So the name by the degree is called a constant. And the number of terms, there's only one term here. So this is called a constant monomial. So the name using the number of terms is just the monomial part. So, but when we put it all together, we say constant monomial. So since there's one term, that's why it's called the monomial. So for the next one, we have a highest power of x is 1, so degree of 1 is linear. There are two terms here because terms are separated by addition subtraction signs, so x plus 3 means there's two terms, and the two terms is a binomial, so we call this a linear binomial. The next one has a degree of 2, so this is quadratic. And so there's one term, so it's a quadratic monomial. The next one we have is highest power of x is to the third power, so this is cubic. And there's three terms, so this is called a cubic trinomial. And for the next one, we have the highest power of x is to the fourth power, so this is called quartic. And there's two terms, so this is a quartic binomial. And then the very last one is the highest power of degree 5, which is quintic. And there's four terms, so we call this a quintic polynomial of four terms. So just as a reminder, things that polynomials cannot have, they cannot have negative exponents or exponents that are not whole numbers. So remember, whole numbers are 0, 1, 2, 3, so basically no fractions or decimals. And remember that for this, a negative exponent, so like if I were to have x to the negative 2, that's really equal to 1 over x squared, which is why we can't have negative exponents. And if I have a fraction exponent, such as x to the 2/3 power, that's equal to the cube root of x squared. So that's, again, why these are not polynomials, because if we have 1 over x squared, that's a rational function, and this one's a cube root function. A variable underneath a radical sign, which we just talked about, because then if we did the square root of x, that would be a square root function. And we can't have a variable as an exponent, because if I had y equals 3 to the power of x, remember this is an exponential function, so an exponential function is not a polynomial function. So for the next part, it says decide whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. So right away, we see we have this x to the 3/2 power, so this is not a polynomial. And why is that? Because polynomials cannot have fraction as exponents. Question number 2 for this one, we see that this is not in standard form. So in order to figure out what the degree and type and leading coefficient are, we need to actually multiply this out. So for this problem, we have two in front. So this is x minus 1 times x minus 1 times x squared plus 1. So we need to FOIL this. I'm going to distribute the 2 here. So we get 2x minus 2 times x minus 1 times x squared plus 1. So we're just going to go ahead and FOIL this out. So the next step, first outside, inside, last. So this gives us 2x squared minus 2x minus 2x plus 2, which when we combine our middle terms there, we get 2x squared minus 4x plus 2, and that's multiplied by x squared plus 1. So for this one, if we FOIL that again, we're multiplying this by the 3 terms. So we have 2x squared times x squared and 1. So that gives us 2x to the 4th plus 2x squared. And then 4x negative times x squared and plus 1. So minus 4x cubed minus 4x. And then the 2 gets multiplied by the x squared plus 1. So plus 2x squared plus 2. So then we combine our like terms, we get 2x to the 4th. We have no other cubic terms, so minus 4x cubed. And then we do have the 2x squared, and the 2x squared becomes plus 4x squared. And then we have this minus 4x and plus 2. So this would be the polynomial in standard form. So yes, this is a polynomial. I'm going to write the answer up here. So yes, and then we want to state its degree, type, and leading coefficient. So the degree, because it's in standard form, is a degree of 4. And the leading coefficient is 2. So we would call this a quartic polynomial. Because it has 4 or more terms. So, and the degree is highest 4. So degree 4 is quartic, and then more than 4 terms is a polynomial. Looking at the last one, right away, if we were to simplify this, we get the root x times the root x, which would be x, and then minus root x. So this is not a polynomial. I can't have a variable under a root. The next part we're going to take a look at is graphing polynomial functions using transformations. So remember that for this one, the parent graph is y equals x to the 5th. So if we think about graphing this, we know that 0 to the 5th power is 0, so we have a point 0, 0. And then let's think about 1 to the 5th. So 1 to the 5th power is 1. So let's just make a quick table. We had 0, 0, 1 to the 5th power is 1, negative 1 to the 5th power is negative 1, because the negative to an odd power stays that way. And then 2 to the 5th is 32. And negative 2 to the 5th is negative 32. So for our graph, let's go ahead and maybe not count by ones, but let's maybe count by maybe 5. So this would be 5, 10, 15, 20, 25, 30, and 35. So negative 5, negative 10, negative 15, negative 20, negative 25, negative 30, negative 35. And then the x-axis will just go by ones. So always label, and like I said, for this, because it's x to the 5th, and I do want more than just the negative 1 and 1 points, that's why I'm changing my scale so that I can have those important points in my graph if you can think about the cubic graph. So we have 0, 0, 1, 1, negative 1, negative 1, and then we said 2, 32, and negative 2, negative 32. my graph would look, oops, it's off there, sorry, here, after the -1, I didn't realize. So our graph will look like that. And so then we have to think about the transformations. So if we have x minus 2 to the 5th power, this is just moving our graph right to. So every point, I'm just going to move right to. And then that gives me my graph. Looking at the next one, so I'm going to rewrite this equation. So we have f of x equals -2 times x plus 1 to the 4th plus 1, because I just moved this to the other side. It's positive, so we're adding it. So for this, we can see then that our parent graph is y equals x to the 4th power, and we're going to look at the transformations. So in this case, because we have x plus 1 inside the parentheses, this tells me I'm moving my graph to the left one first, and then we're going to move our graph by a reflection across the x-axis. And we also have a vertical stretch by 2 and up 1. So for my parent graph, let's think about plugging points. So 0, 0. If I plug in 1 or -1 to the 4th power, so 1 to the 4th power is 1, -1 to the 4th power is also 1. And then if we did 2, 2 to the 4th power gives me 16, and -2 to the 4th power is 16. So let's count by 2's on our scale here. My x-axis, I'm just going to again count by 1's. So on my graph, we have 0, 0, 1, 1, -1, 1, and 2, 16, and -2, 16. Then we're going to move our graph left 1. And then we want a vertical stretch by 2. So remember, that means we're going to multiply our y values by 2. Or actually, let's do that. Sorry, the reflection across the x-axis first, and then we'll multiply. So reflect across the x-axis. The graph would look like this. And then a vertical stretch by 2 means that our graph is going to be down really far. So negative, we have to point -2, -1. So -1 times 2 would be -2. So that would move that point to there. But then, of course, the next point is at -16 times 2 is -32, which is just going to be way far down. And then the last step would be to move our graph up 1. Just all kind of right in there. So that would be our transformations made to our graph. Next, we're going to look at the end behavior. So the end behavior describes the behavior of a graph as it becomes infinitely large and infinitely small. The limit is the value the function approaches as the input of the function approaches some value. So we're going to use limit notation for our end behavior. So the limit notation looks like this. We have the limit, and underneath it in the subscript, we have x approaching something either positive or negative infinity. F of x, remember, stands for your function. And then if it's going up or down. So we're going to look at what these different values are approaching. So last year we used the notation like as x approaches, let's say, infinity, f of x approaches infinity, etc. But now we're just taking this into this limit notation. So instead of writing it like this, we would write as x approaches infinity, f of x approaches infinity. So this says the limit as x approaches infinity for the function equals infinity. So it's just a different way of writing the notation from what we learned last year. So let's go ahead and look at the degree, odd, and the leading coefficient positive. So think about when you have an odd degree. The smallest odd degree you have is y equals x. So what does y equals x look like? It looks like a line that goes through the origin like this. And so it doesn't matter what the degree is. Anytime you have an odd polynomial degree with a leading coefficient, the right end of your graph will always go up and the left end will always go down. So the way that we write this notation would be the limit as x approaches, let's do negative infinity first. So negative infinity for your function is equal to negative infinity, just going down. And the limit as x approaches positive infinity for f of x is equal to infinity because the right end goes up. So the left end goes down and the right end goes up. So on the next one, same thing. We're going to do an odd polynomial degree, but this time we're going to do the leading coefficient as negative. So if this is odd negative, think about your smallest odd negative, y equals negative x. So now our line would go with a negative sloping direction. So this is what our line would look like. So now you can see that the right end is going up and the left end is going down. So the limit as x approaches negative infinity for the function goes up towards positive infinity. And the limit as x approaches positive infinity for the function goes down towards negative infinity. Then next we have even and odd, or even degrees. So we just did odd. So even with a positive leading coefficient. So this would be y equals, let's say, x squared. So we're just thinking about the smallest graph that we have. So y equals x squared would look like this. And so for this graph, we can see that both ends go up. So that means then the limit as x approaches infinity for your function goes to infinity, and the limit as x approaches negative infinity for the function goes to infinity. And you can actually write this together. You can write the limit as x approaches plus or minus infinity for the function approaches infinity. Any one of those would be acceptable. And then let's say we had an even degree with a leading coefficient that is negative. Then if you think about your smallest graph, you have y equals negative x squared. So for this one, both ends of your graph, we know that your graph is just going to go down direction. So both ends go down instead of up. So for this one, the limit as x approaches negative infinity for the function approaches negative infinity. And the limit as x approaches infinity for the function again goes to negative infinity. And you could write them together like we did in the last one. It's just a personal preference. So now just it says what's true about the degree and leading coefficient of the polynomial function whose graph is shown. So if we look at these, you can see both ends going down. So that means this degree has to be even with a negative leading coefficient. This one, the left end up and the right end's down. So this one was down, down. This one is up, down. So we know this has to be an odd degree because they're going opposite directions. And we know this is a negative leading coefficient because the left end's up and the right end's down. So this one we have down and then up, which means this is also odd. The leading coefficient would be positive. And when both ends go up, we know this is even with a positive leading coefficient. Now in the last part, it says we're going to describe the end behavior of the following functions using limit notation. So for this one, Now, keep in mind if it's not in standard form, you always want to look at it and think about it in standard form. So for this one, if we think about multiplying all of our first terms out, we would have 4, and then the first term here would be x to the first power, and this is also x, but notice it's to the third power here. So think about multiplying those out, because if we were to FOIL all this out, it might take us longer. It's easier just to look at those first terms. So we have 4 times x to the first times x cubed. So if you were to multiply this out, your first term is going to be 4x, and when you add those exponents, you get 4x to the fourth. So that is my lead term. So that means the degree would be a degree of 4, and the leading coefficient, which is the number in front, is also a degree of 4. So that means this is going to be even, positive. Both ends go up, so we can write the limit as x approaches plus or minus infinity for the function goes to infinity. Looking at this next one, again, same thing, it's not in standard form. So you can FOIL this all out if you want. It's just going to take you a while because you have x minus 5 to the third power and x plus 4 squared. So instead of having fold out, let's look at all of our first terms. So this negative means there's a -1 there, times this would be x to the third power. And this one, when we multiply out the first terms, you would have x times x, which should give you x squared. So this gives us negative x to the fifth as our lead term. So the degree is 5, which is odd, and the leading coefficient is -1, which is, of course, negative. So if we have odd negative, that means the right end goes up, or excuse me, the left end goes up and the right end goes down. So that means we have to write this one separately. The limit as x approaches negative infinity for the function is approaching infinity, and the limit as x approaches positive infinity for the function, since the right end's going down, goes towards negative infinity. So looking at the next one, again, making sure you're in standard form. So this is in standard form, so we can see that the degree is 2, which is even, and the leading coefficient is -8, which is, of course, negative. So even, negative, both ends are going to go down. So the limit as x approaches plus or minus infinity for the function goes to negative infinity. For this one, we can see that this again is in standard form, so the degree is 7, and the leading coefficient is that 4 that's in front. So this is odd positive, which means that the left end goes down and the right end goes up for our graph. So the limit as x approaches negative infinity for the function, since the left end goes down, is negative infinity, and the limit as x approaches positive infinity for the function goes to infinity, since the right end would be up. So that is it for our first lesson on the polynomial units, making sure you know what the names are by degree and number of terms, making sure you know what a polynomial is, like how do we know it's a polynomial equation, how to put it in standard form by multiplying full-like terms, transformations still apply, and also the end behavior.